Now the second case we have with these are projectiles launched up at an angle. Now for these ones here, the vertical motion is going to be exactly the same as if you take an object, you throw it straight up into the air, and then it reaches its highest point and then comes back down. And so we did those sorts of problems then in our kinematics unit. What we're going to do with these then is we'll treat it like that in the vertical component, and then we'll also of course have the horizontal motion there. Now for an object that's just thrown up and comes back down, again, the gravitational force and the acceleration due to gravity is the only thing that's acting on it. And so if something's moving through this projectile path, remember that the only force is the force of gravity, and so the acceleration and that downwards force then is going to be the same for those as well. Now we do still have this horizontal velocity. It's independent of the vertical motion. It does mean that it ends up landing kind of way over here, so it gives it a different landing position, but the vertical motion is going to be exactly the same. And as before, don't forget your acceleration is constant all the way through, and that's at 9.81 meters per second squared. Now the way that we approach these questions is going to be the same as we did with our horizontal launch. And so what we want to do is we're going to split the motion up into horizontal and vertical components. Now the really only difference here is that we really have to watch for direction here. So in our horizontal component, where we have that one directional motion, everything's in one direction, so we'll use the v equals d over t because there's no acceleration, and we'll keep everything as positive because we have only one direction to the motion. In our vertical component though, we're going to be first heading upwards and then coming back down, and so that means we're going to have two directions. And so we do need to always designate either up as positive and down as negative, or vice versa, and really watch your signs when you're going through there. So the acceleration is always down because it's always the force of gravity. Vf and Vi though, those can be in different directions there, and then your distance can also be in different directions. So watch carefully for those. Time is a scalar, so it's always positive. The other big difference with these ones here is that our initial velocity vector is now no longer all in the horizontal component because it's going to be launched upwards. And so what we're going to have is we're going to have two components. So we'll have to take our velocity vector, and it'll be launched at some angle here, and the angle will always be measured, of course, from the horizontal. We'll have some x component and y component then to that motion. And so the y component is always based on sine. So you could derive this each time, but you can jump straight to here as well. So the actual velocity of the object times the sine of the launch angle will give us then just the vertical component to the velocity vector. This is the initial velocity vector. And then the vx, which will be constant all the way through, which is the adjacent side, always comes from the actual velocity vector, so that's up at that angle, times the cosine of the launch angle. And that'll give us then the horizontal, or vx. So look at a few examples here then. So we have a soccer ball that's being kicked downfield with an initial velocity then of 14 meters per second at an angle of 65 degrees upwards from the ground. And we're going to start by looking for the maximum height reached by the ball there. Now the maximum height is going to be, of course, in the vertical component, and we actually for this one only need that vertical component. And then we'll look at how far downfield it goes, and for that we'll need both of the components. So if we look at the ground, first of all, the path that it's going to be taking is just going to be that ballistic trajectory, so something along that path there. And I'm going to have this initial velocity vector then heading up here. Now remember that in the vertical component, at the very highest point reached, so that's going to be this one over here, that's going to be the case where the vertical velocity vector is going to be equal to 0. And so that's going to be then defined at that highest point there. So this initial velocity vector, I do need to take that into 2. So at this angle of 65, so heading up at 65 degrees, that's going to be the 14.0 meters per second. What I'm interested in is what are the x and the y components to that. And so I have the x component along here, and the y component then along here. And so when I solve for each of those, well, in this one here, we're just looking for the y actually, so we'll just jump straight to there. And so my v and y is just going to be then 14, and then it'll be sine times the 65. And so that'll always be true for the y. We'll take the actual velocity vector, and then that'll be that vector times the sine of the angle, because the y is always opposite then of the angle. So if we look at our vectors then just in the y component here, I have then the vi, so that's the initial velocity, equals 14 sine 65. Now I could solve for that right away, but I'll just leave that as a variable for a moment. My vf I know is going to be equal to 0. So remember, we're looking at the highest point then in the flight there, so that'll be a vf equals to 0. Now we're looking for what that distance is going to be. We also know that the acceleration is going to be negative 9.81 meters per second squared. I'm going to make that one negative because this 14 sine 65, I've made this one a positive, which means that I'm taking up to be my positive direction, and initially that velocity is positive. So make sure you're putting that a there. It will make a big difference then to the final answer. So I actually have enough information here. I don't even need to solve for time. I have enough information here to figure out what my VF or my D is going to be, and so I can use that VF squared equation. So VF squared equals VI squared plus 2A and D. Now my VF is going to be equal to 0 at that highest point, and so I'm going to get then negative 2AD. If I just subtract that 2AD to move that to the other side, equals VI squared. And if I'm solving for D, I'll divide out the 2 and the A. Actually, divide out the negative, the 2 and the A. I can put my values in for there. My VI then was at 14 sine 65. I'll just put that right into my calculator there, but you could solve it as a value, of course, as well. Don't forget to put that whole thing in, close the bracket, and then square it. I'll take negative 2 times, and here's where that negative comes in, negative 9.81. And those two negatives then will make a positive, and that gives me a positive displacement. And that's what I'm expecting because I'm ending up at the highest point. So I am ending up higher than when I started, so I should have a positive displacement at the end. If we put those into our calculator, we get 8.21 meters as our final displacement. Now for the second part of this, we'll look at how far downfield did the soccer ball land. And so here we're going to need then the horizontal component. Now we can easily find then the horizontal velocity vector. That's just going to be the 14 cosine 65, and it'll always be based on the cosine there. But we'll need to find the time that's in flight in order to find the distance. Now we can find that time from the y component. Now there's two ways that we can go about doing this. One is we can just find the time based on this set of variables that we have here, where VF is equal to 0. If you do that, just remember that we're only going to the highest point here, which is only half of the motion. Now as long as you recognize that that's fine, you can solve for the time and then just double it, because the trip up will be equal to the trip down. So that's certainly one way that you could do that. Just solve for the time using these variables and then double that time. And as long as you remember to double it, that'll work out fine. The other way that you can do this is just recognize that the trip up and the trip down are the same. So whatever the velocity is over here is just going to be equal and opposite over here. So that means if my initial velocity is positive 14 sine 65, at the very, very end, my final velocity will be negative 14 sine 65. And if you solve it that way, then you'll just end up with the total time just basically in one shot. So I'm going to solve it like that. But again, it works fine in both methods there. And so here in the y component, and then we're going to use this to solve for time, our VI will be that 14 sine 65. And then our VF will just be minus that, so negative 14 sine 65. We're looking for then an acceleration of negative 9.81, and again that's always in the downwards direction. And what we're solving for is time. Now we could also put in displacement of 0, but if we're looking for time we don't need it, because we can just use VF minus VI over A to give us our time value. And so then VF minus VI over the acceleration. On your formula sheet is A equals VF minus VI over T. I just rearrange those then right away. So, and watch your signs carefully. I'm going to have negative 14 sine 65 and minus from here, and then a positive 14 sine 65. If you forget the negative sign, this will end up being 0, and that should be a good indication that you're doing something wrong, of course. Now this will give us a negative in the top. Our acceleration is negative in the bottom, and so that will give us then the positive time, of course, that we're going to be expecting. And so that'll give us then 2.586. And it'll, of course, be in seconds. So once I know my time, then I can go to my x component. And so for my x component, remember that we do still have that initial velocity vector. And so if my actual velocity is 14 along this path over here, the horizontal component to that will be the adjacent side of the triangle, and so I'll end up using cosine for that. And so the velocity, now we don't need VI here because there is only one velocity in the horizontal component, that'll be 14 cosine of 65. And for these ones here, the velocity vectors in each will always be then cosine for x component and sine for the y component. The time then I've just solved over here, so that's my 2.586. And then I'm looking for how far downfield then This is gone. And so as before, d is equal to just vt. So these are always going to be the same for those because there is no acceleration. And so my distance equals 14 cosine of 65. And then multiply them by that 2.586. And then when you run that through, you'll get 15.3 meters. So when we're given the maximum height and the distance downfield, and we're looking for then the initial velocity. So what this is going to mean that we have to do is we need to find then the two components. So we can use the maximum height to find the initial velocity in the y component, and we can use the total distance downfield then to find the total velocity moving downfield or in the horizontal component. Once we know those two components, then we can combine the two then to get the initial vector here. So if you look at just kind of what's going on with the football, again, we'll follow the same kind of path, and I'll follow this sort of path down here. Now what we're looking for here is we're given then the maximum height. So our maximum height then is going to be 24 meters. And then we're also given the total distance downfield, so that's our horizontal displacement. That's going to be 78. Now what we're looking for is this vector over here. Now this vector, of course, though, is composed of two. So if we can find this horizontal vector and the initial or vertical speed vector, we can easily combine those two to get to here. So that's what we're going to be looking at for this one. So we'll start with the variable listing then for our vertical component, and then we'll solve for that vertical velocity based on that, similar to the last one we did. Then we'll be able to do the same thing for the horizontal, and then we can combine those two. So if we start with the y component, a couple things that we always know. Now if I'm using this displacement of 24, which is what I have for my vertical motion there, so I'll use that one. That's going to be to the highest point. So if I'm using that value, then I can also use my VF equaling 0. And I don't know what speed it's going down here, but if I go to the highest point with the 24 meters, I can use VF equals 0. Now what I'll be looking for then is the VI. Now that's only the Vx and the y component, so that's going to be this red line over here. So I'll be looking for that. So I also have my a value. Now it's going to be negative 9.81, and again I'll take up to be my positive direction and down to be my negative direction. So in order to find the speed then, I can just use the VF squared equation, and so I'll have then VF squared equals VI squared plus 2a and d. Now this one here, as before, I get a 0 there, so I get negative 2ad equals then that VI squared. And so if I'm looking then for the VI squared, I can just take the square root of that. So I'll take the square root of this one here, I get negative 2. Now watch that negative, I can't take the square root of negative number, but since my acceleration is negative, that'll work out okay. So negative 2 times negative 9.81, and then times my distance of 24. Take the square root of that, and that will give me then the VI. Now remember, that's the VI just in the y component, so that's this red line here. It's not the total VI that I'm ultimately looking for here. So the VI then, again, in that y component, if I put that through my calculator, will be 21.69. And that'll, of course, always be in meters per second. And we'd recommend always dealing with meters per second in these questions. Now, to solve for the x component, I'm going to need to go then to the to find the time. Because in my x component, the only value that I have is going to be then the 78 meters. So I know the distance there being 78 meters. If I'm going to solve for the velocity in there, I also need to know the time. And I don't have enough information in the x component to find the time, but I can find the time, of course, in my y component. And so for this one here, once again, we can do this in one of two ways. We can take my VF as being 0. That gets me to this highest point. That's half of the overall motion, and I can just double that. Or again, we could just take the 21.69, and then in negative 21.69, I can use then the equal and opposite beginning and end points. So here I'm going to solve it actually just to my highest point, just so I'm doing it a little bit differently. And so then if we look for our time here, and again, remember that's time to this point over here, which is half of the total trip, we can solve for that. Now we'll use the same equation for that. So we'll use t equals my VF minus VI, and that's all going to be over my a value. Let's go up here. And so my time here, now this is the time to the highest point, and so my VF is going to be 0. Now my VI I know, so I solve for that over here, so it'll be negative 21.69, and then all divided by the negative 9.81 meters per second squared. And when we run that through, I'll get 2.21. Now that's at the highest point, and so my time total is going to be twice that. And so again, you can solve for the highest point time and then just double it, or we could have also put into here, instead of the 0, we could have put in a negative 21.69. And that'll work out the same either way. We'll get 4.424 seconds. And again, more numbers at the end there, so just hold the numbers through in your calculator all the way through. So once we know this time, and again we need to know the total time then to get up to that 78, so then we can put that in for here, and now we can very easily solve for then the x component for the velocity, because the velocity is just going to be distance over time. Now this is the velocity, of course, in x, so the velocity in x will be a distance then of 78 meters all over top of a time of 4.424 seconds. And so my Vx then at the end of that is going to end up being 17.63 meters per second. And what that gives me then is it gives me this horizontal speed. So the Vi that I have over here, that's the Vi just in the y component. That's this red line over here. And this Vx that I found over here, that's then this green line over here. And now what I'm ultimately interested in is what is the actual velocity of the football when it was kicked. So I can now combine those two in a triangle to find the net. So my net velocity vector is going to be something like this. And so then I'll have this horizontal one over here and the vertical one over here. Now this vertical one is 21.69. This horizontal one is 17.63. Now because I'm looking for the velocity, I'm also going to need this angle as well as the magnitude then of that vector. So I can get the magnitude of that just using Pythagoras' theorem, and so that'll be my V net for my total initial velocity. And so my V net squared will be equal then to the Vx squared plus then that Vy squared. And so for my V net, I'll just take the square root of the 21.69 squared plus then the 17.63 squared. And then if we put that values in, or those values in, then we'll get a V net of 28.0 meters per second, and then we can round to the 3 significant digits that we have. Now if we were asked for a speed, that would be enough, but we're asked for a velocity, so we do also need this angle, and so I'd use tan for that. And so tan of theta is going to be the opposite, which is the 21.69, over the adjacent, which is the 17.36. So 21.69 over 17.63. And so theta then is going to be equal then to the inverse tan. And remember, when we're solving for the angle, we use the inverse tan. For given the angle, we use the regular tan. So 21.69 over top of 17.63. Put that into our calculator, and we'll get an angle then of 50.9. And that'll be from the horizontal. So we'll be at 28 meters per second at 50.9 degrees from that horizontal.